Welcome to the computer vision. Today we're going to talk about 1D filter, and I'm going to take you through various ways that we can apply filter to a 1D signal. For instance, how we can scale the signal, how we can slide windows so that we could calculate the filter based on neighbors per location. And then we'll talk about what cross correlation means and what does it mean by convolution, how can we calculate, and what is the Lapacian filter, and how can we use filter to shift the signals, and some of the activation like ReLU and nonlinear function like Maxpool. It will do this by hand to build intuition, and then we'll go through larger scale examples and we'll actually code it up and to gain the further intuition. All right. All right. Going back to our hand tab. So first, uh, I would like to talk about how we could change the signal. For instance, change the magnitude of the signal. If we like to scale signal up, for instance, by 4 times. So we have this, we can arrange in this way. And then we'll basically just multiply 4 times 1. So 4 times 1, 4 times 6, 4, you get 15. Sorry, 16, and 4 times 3 is 12. So this is relatively easy. 4 times 4, 4 times 4 is 16, and 4 times minus 2 is minus 8, and 4 times 6 is 24. So you can see this like one-to-one mapping from our input to the output from X to Y, and signal at every single location over T, or if it's a time series from 0 to 15, is magnified by 4 times, and we see this one-to-one mapping. So in order to figure out the new value, for instance, 16, we only look at the input value itself. We do not have to look at the neighbors. And so, and if we would like to consider neighbor and to account for the impact, use neighbors and context to be to derive a new signal, more informative of the features around the location. So we'll use that idea, just called sliding window. For instance, if we have this location, the first location, and then we could consider neighbor, and then we can rearrange the neighbor and into the column vector like that. It'll become clear to you in a second why we like to arrange them into column vector. And for this second window position, so there will be 1, 4, 2, kind of like this, or simply do 1, 4, 2 to rearrange them into a column vector. And this worked it out for this location. We'll take this window size 3 and 2, 4, 1 in this case. And then let's do this one. So this window center at the particular location. So 4, 3, 5. Another one. So just practice a few times. If quickly you get the hang of it. So this is a way that we can bring in location in the neighboring, bring the neighborhood with respect to a particular location. So, and then something you can pay attention to is that when we collect window, there are some kind of boundaries if outside of the bound. So when we collect neighbor, we might have this not a number situation. So if you think about how you would like to handle this situation, for instance, we can add new value that's called padding. We'll pad the value so that we're not gonna get a non-number, we'll get an actual value. And so in the next example, next topic we'll look at is this idea called cross correlation. Once we arrange each neighborhood or each window into this column vector, then we could compute the correlation between a filter and the particular window. In this case, we can take care of the boundary out the boundary by padding a new number. I add minus 99 to just make it really obvious. It is something we padded. It's not from the original signal. And for cross correlation, this idea is that once we, for instance, want to calculate this value as a result of taking a cross correlation between this window, and then we convert it into a column vector over here. And suppose we have a filter H, and the value is 1, 2, 3. And to compute cross correlation is basically taking the dot product between this row and column vector or maximum multiplication between these two. So for instance, get this one. And we have done this operation multiple times already. So just as a review, so 1 times 1, we get 1. 3 times 2, we get 6. 2 times 3, we get 6. When we add these three up together, then we get this 13. That's how we compute this value. And for this one, can do that faster. So this 4, because 4 and 1, 0 and 2, we get 0 and 2 and 3, we get 6. So this value is 10. And all the other value are calculated the same way. All right. And so for this, and so with and so the cross correlations that if we write up the equation is usually we have a filter H, and then we can use this symbol to denote cross correlation. And this is going to be our input. And we run this X kind of along, scan along the signal. And then in this particular arrangement is that instead of just writing a for loop, if you just most intuitively, the most basic way to implement this is actually write a for loop, just loop through that. But the way that we can rearrange this in this column format, basically turn the signal into this series of columns that are concatenated horizontally together. That is because then we could take advantage of match multiplication, this cross correlation, sliding windows iterative operation, taking many steps, becomes a one big match multiplication. You can put it on GPU for a lot of efficiency gain. So that's the idea of why you like to do this conversion. So they could calculate all this correlation at once in one batch very quickly. And so this is another way to write this. We want to sum over every location of H set U and with every time T, kind of similar to something like this. But we'll break the equation down later in the second tab. But for now, that is one example of cross correlation with a particular filter H123. But if you change the value to other value for H, you could basically repeat the calculation just by taking the maximum application at every single location. All right. So another really common way we could run cross correlation is we have a sum filter, 1, 1, 1, and the effect of having a sum filter basically add these three numbers together. So we have 1, 3, 2. So if you have this filter 1, 1, the outcome is basically sum of the three numbers. So how can we calculate the mean? So there's a very common filter called mean filter. Basically, instead of 1, 1, 1, you get 1/3 because there are three. The window size is 3 in this simple example. 1/3, 1/3, 1/3. So we take the dot product between the two for this particular window. There's going to be 1/3 plus 3 times 1/3 is 3/3 plus 2 times 1/3 is 2/3. When you put it all together is 2. Because 6/3 is 2. Okay, so that's how we'll calculate this value. And all the other ones that follow a similar principle of taking the mean. So just take one example. This is the mean of this. Okay, right? 6 and well, let's just check it. 1 plus 5, 6. 6 plus 6 is 12. 12/3 is 4. Okay, so this is this is what mean filter does, and this is a sum. Okay, just write another one. So this is sum, just to emphasize the purpose of these two filters. And another term that we use commonly is convolution. So there's a common notation is we have a filter called or a kernel called H, and convolution we can use this sign, the circle with a star in it, and this with a signal. So this convolution. And it turns out the way that convolution can be implemented is that you can convert them into a cross correlation. So by flipping the filter. So if we flip the filter for some reason and it becomes cross correlation, that equivalent to calculate the cross correlation. And if you are taking signal processing, you'll probably spend the next hour trying to listen to your professor and look at the proof. But since we are computer vision, so we're just gonna give you a takeaway. Basically, convolution is a flipped version of correlation with respect to the filter. So in terms of calculating it, so suppose we have convolution a filter H, we want to convolve that with our input signal. So the first step is that we could convert them, flip it to 1, 2, 3, and becomes 3, 2, 1. And now the rest is exactly the same as cross correlation. Basically, we could take the dot product between the corresponding location. So in this case, we can take the dot product of this row and column, and we get 3 plus 6 plus 2. Again, now you have done enough of this. You could, this should be, is it right? 3, 2, 1, 3, 6, 2 is 11. Is it right? Yeah, 11. Okay. Did I make any calculated mistake at the top? 11. Okay. And then if we split for some filter, if we split a sum filter, you might immediately notice that after you have written down the three numbers, they're exactly the same. It turns out if you have a filter that's symmetric, the flip version of the symmetric filter is itself. So for a symmetric, in other words, so for symmetric filters, convolution and cross correlation are kind of somewhat interchangeable, could be used interchangeably, and but they are not the same. But it's in case because it's a symmetric filter, they are same. So we know this is going to be a sum of the three numbers 1, 3, 2, and for mean is also going to be exactly the same. So the value should be the same. So you compare the previous example, it's 1362. And in this case, it's 1162. For first filter, the results different, but the second and third filter result are the same. Okay, hopefully that so you could help you remember that. And so convolution versus cross correlation. And then next we'll like talk about Laplacian filter. And Laplacian filter is based on the second derivative of your signal. For instance, we have a second derivative of a signal, and that if that is kind of zero, it means that there's some sudden change of so you're kind of going up and then down over here. So that's where that equals zero. It means that you could be at the top of this kind of the intensity change. It usually looks like an H in your input signal, or in the 2D case, it looks like a line. Okay, so and so in the discrete case, for this window size of 3, and there's this set of number we often use to achieve that purpose, to to be able to discover places where there's a zero, and there's a lot of proof for that, but we're not gonna go into that. But -1, 2, and -1, you can also see that these three numbers add up to 0. Okay, so this particular pattern can help us pick up the area that we have with big signal change. You can see here 2, 10, 2, where there's a signal change here, and they will expect to have pretty high Laplacian value. Okay, so I think, and then in this case, I could pad this. And I realized my example is not, so 1, 1, 2. So this is actually 1, 1, 2. I have an off by 1 error in my example, but I can fix it real quick. So in this case, it's 1, 2, 10. So it's 1, 2, 10. In this case, it's 2, 10, 2, 2, 10, 2. Okay. All right. So, but then let's compute this one. So 1, 2, 10, we get -1 plus 4 minus 10 is going to be, what is it? -3. Okay? Is it -10? -11, -7. Sorry. -7. This is -7. Okay, I think I off by 1 error. So this is a -7. But the next one, 2, 10, 2, is going to give me, let me write it down here. So -2 plus 20 minus 2 is going to be 16. You can see that this value is kind of 16. So there's a bit higher. That correspond to this particular signal change. So let's find another area where something high here too. This is high. And so this can kind of correspond to this error, but they'll have off by 1 error in my example here. But you get the idea. So this is how I can calculate Laplacian by just this -1, 2, -1. But then if we get to rearrange your 1D signal into this window, like column form, you'll be able to just take this. So I think the way that I can fix this is I could, even though I'm supposed to be code here, so later, but I just want to fix it now. So I can delete all this. So all I want to do is I want to set this one to this window, But before I can commit to this, one more time, like this window, but I also, please, you can see that it goes horizontally, so I can two column to fix this one. All right. And once I have this one, I can just copy and paste and paste and paste, paste and paste and paste, and or just paste everything. You say, I don't want to paste this arrows. I just erase all these arrows that I didn't mean to paste. Okay, now I fix this. And then I go down here to fix this. I think I select the, okay, this already fixed. All right, so now it's a 16. Do you see the 16? That's what I calculated. And for maybe just calculate this one for the sake of completion. So it's 12 minus 12 plus 6 minus 2 is minus 14 plus 6 is 8. Okay, so that's how we calculate Laplacian filter over a 1D signal using cross correlation. And then we could also use cross correlation to shift. In this case, I want to have a larger window size of 5. So suppose in the first example, I would like to shift the signal to the left. So the 1, 2, 3 one shifted to the left by 2. So what would be the signal of the filter H1 is to shift left by 2. And then just erase 5 here. And then for H2, I would like to shift right by 1. But it turns out when shift left by 2, we want to have 1 over here and everything is 0. Basically, what it says is that I would like to, this is my center. I want to shift left, meaning that whoever is to my right by 2 spots will all of a sudden become where I am. So this is the kind of idea. So if shift signal by left, meaning the 2 neighbors down to the right will move to where I am now. So by similar logic, if we want to design a filter that can shift the signal by 1, so we can select the 1, 2, the neighbor to your left. So this is a signal I want. And once we do that, and we just do a little bit sliding window arrangement here. So in this case, I would like to pad. So you can see that one of the padding techniques, we copy the value. So instead of just using minus 99 as I did in the previous case, in this case, if we use copy as the padding technique, in this case, could arrange my first window is like about here and is it here? So 1, 1, 1, 2, 3. Okay, how about this window? This window center over here. So this and this is going to be 1, 2, 3, 20, 21. And then if we multiply this, and so you can easily see only this is being multiplied, right? So it's going to be 3 and 21, follow the similar logic. And then you can see that it's going to shifting to the left, signal shifting to the left by this 3, 20, 21. So by similar logic over here, so we have shifted by the right by 1. So we'll pick this to this location, as you can see here, similarly from this location. So we get 1 and 2, and you can compare these two signals. One actually comes from these things I padded it with. I think it's getting kind of, I think it's just even the one that's over here, and 1 is over here. 2 is over here. So you can see the signal shifted to the right. By shifting to the right, you're going to introduce these things you copy with. And instead of minus 99, you get 1. So the signal at this boundary doesn't have this discontinuity issue. All right. So the last by hand example we're gonna go through today is some nonlinear transformation. That the first one we look at is ReLU. You might have heard of ReLU in the context of deep learning, but ReLU is originally invented somewhere else, of course. So that idea of ReLU is that if we have a signal, suppose we have 1, 2, 3, everything that's kind of above 0 we keep. So 3 we keep. Below 0 we don't keep. We stay to the 0. All right. So keep, no, don't keep, or suppress it or deactivate it and keep. If you do just one time, immediately you understand what ReLU really does. Okay, and then for Maxpool is that you would consider the neighbor in this case, or want to have a neighbor of window size of 5. So then I take my input signal. Let's use a different color so not too ugly here. So with the signal here, I think what I intend to do is to so to take the result of ReLU y1 and to convert to y2. So x becomes y1, y1 becomes y2. That's my goal. So we'll take this window this is the window of 5 position. So 1, 2, 3, 0, 9. And another window is this much. So 0, 9, 7, 0, 3. And then eventually I take the max, find the max value, maximum value within each window. So this case is going to be 9 because 9 is the biggest. In this case, also 9 is 9 is biggest. So the resulting signal is 339999. So we look at ReLU and max. One thing you notice that if you compare to the example above, we have a filter. We have this weights 1, 2, 3, 1, 1, and this. So these are to allow you to perform linear transformation. If we perform a matching modification in order to calculate the output. But for ReLU, does not have any parameters. So ReLU does not involve parameters. There's nothing here to our left, no parameter. So it's Maxpool. There's no parameters. Basically, you pick the window, and you have this window size actually hyperparameter. You don't actually train for. So they will revisit some of these issues, this nuance later. Okay, so this is the end of the hand tab that will. This is it was hopefully that you could follow the calculation, and if you repeat it in your study, then you could really get down into intuition behind some of these operations in a 1D case. And when we come back again in the next lecture, we'll see how we can extend this concept into 2D case. That's actually our goal. This is just like a intermediate step. We're trying to use 1D case to help you establish some of these fundamental principles. All right. So let's look at the Excel version, and we can bring it up to notch and actually implement this. So I prepared this example, and with this 1D signal visualization, all of this case is like we're trying to convert map a signal from X to Y in some way. And this scaling example, so we have defined a scaling factor, say we put a 40 over here. And so for this case, I would like to do 4 times the signal. And we can use the array formula, basically the whole thing, then we get this. And you can see every signal here is being magnified by 4 times, proportional to what the signal is originally. So if you have signal bigger, after times 4, it becomes even bigger. And if you have minus, you're gonna go more down and so on, okay? So that is scaling. And then in this case, it does not involve any window. And then in this case, next case is actually does involve sliding windows. So we talked about instead of writing a loop, if you have a loop iteration, you have to run 15 times at the CPU. But if you fold them, unfold them into this form, and then we could just use a GPU to calculate this as a large matching application. So to implement this, first, I think I did this already. So I would like to take this as a window size of 3, and then you can see that it is not in the right orientation. So I got a 2 column to turn it into a column. So once we have that, I can copy over here to the next location, to the next location, to the next location, to the next location, and so on. And then I can just copy the whole thing over here. All right. So notice that I purposely left my not a number there just to make a point that we have to account for the boundary things at the edges of the signal. So in this case, now I have a sum. Sum filter is 1, 1, 1 to sum them up. But there's not a number, and 1, 4 cannot be summed. So I'm gonna just start from here. And then to make the point that now I can just treat this correlation across all these location, cross correlation across all location is a maximum multiplication operation by showing you this is an equation formula I'm going to write. Maximum multiplication with h and x, I mean m, M is the reformatted version of X based on the window. So they can see now I have the summation over the three locations. It's a little bit average, kind of like following the similar trend of the signal. And then now we can look at the mean, which is very, very similar to the above. So I just do it real quick. A two column, come on, two column, and one more time, two column, parentheses, select one, three of them, okay, and copy them to the rest of the location. The copy, I use copy formula this time. And then in this case it's one third, one third, one third for my mean filter. And then in this case, I want to do my match marcation, but ignore the first spot because first, without padding, the first location is going to be invalid and the signal actually shrink because we didn't pad it. If we choose not to pad it, and then now you can actually see the effect of the mean filter. What do you observe? So the orange is our X signal, and Y is our output signal. And you can see that Y kind of somehow follow the smoother version of your X signal, right? So one of the effect of mean filter is that you kind of smooth the signal out just evenly across the three locations in your window. In and the next is Lapacian filter. Lapacian filter, one of the purpose, one of the effect is to be calculate this like changes over here. We want to see some captures. This is input signal captures something over here. I want to see higher signal for Laplacian. And then, so this is something you kind of memorize. So the Laplacian filter in the discrete case, and the smallest one in the three, for window size of 3 is going to be -1 and 2 and -1. All right, something you just kind of remember. And now this case, I want to pad with copy, which I already did. But if I can implement it, I just deleted it. If I remember it, I just stated, refer to the previous one. So in this case, similarly, I just stated to refer to the previous one. So if I change the signal to something else, it's just gonna change the signal, okay? All right, so now I can implement my window. So I'm gonna do quickly again. I can do so many times, but by the end of this, you kind of have it. Actually, no, I put in the wrong location. Let's do one more time here. Two column, and then select three of this. And then once I have that, I copy the formula and paste. Copy, and I paste all the formula into this location. Now I have transformed into this format in this matrix that, well, the column, the concatenation, very horizontal concatenation of the column of the windows. Okay, and then next I could do the multiplication. Instead of had to skip the location because I padded it, I could select the entire thing. And nice thing is after I pitted it, I can preserve the signal length. I got 16 and I also got 16 out. I got 16 in, 16 out. Whereas in the previous unpadded case, I got 16 in, but I only got 14 out, okay? So this is the example. And you can see that, so the blue are my output. If I use the blue, maybe use the blue here. So this is can see that this is kind of high location or for high responses to Laplacian filter. It does correspond to this. We purposely have this peak is over there and to capture the case. This is where things kind of go all of a sudden abruptly go up and then stay there. Okay, so you can see the expert Laplacian. Now I can play with the shifting, just this time with the 5 of them. So this column. First, I want to do the conversion into this format, in the current format of my input signal. And I copy them over again, formula, and I've done very quickly. And so for the shift, the first I want to have a shift right. So shift left by 2. So I can do shift left by, actually shift left by 2 is like this. And shift right by 1 is like this. This from our previous hand tab. And so that once I have this one, what's nice is that I could have performed this by instead of just one filter at a time, I could do the 2 filter together. And with my input tensor or matrix in this case, And then just make one match multiplication. You don't see any loop here. No iteration, no for loop, no double for loop, no triple for loop, just one match multiplication. And once they can see that we have input, orange is our input signal. The blue one is Y1. Y1 shifted to the left kind of like this, okay? By 3. And gray is shifted to the 1, is our Y2 shift by right by 1. So it does make sense. So you can play with it. So if it can kind of one like this, you can shift, both are shifted by 1. You can also say what happens if you do a bit more, kind of shift to the left and right, but you also average these two locations. Sum them together, but not averaging, sum them together. But you can just play with it. Kind of, say if I do this, what does it mean? I'm shifting to the left, kind of, but average two signals locations, kind of like this. And we can do something similar because, okay, I'm actually paying shifted signal to the right, but I trying to average two locations, two time point, and trying to do that. So this is as a way that I just type in different number in. I'm showing you how, as a human like myself, I could design this filter to achieve certain output I want. And next, I would like to show that to talk about a very common application of being able to run a filter over a signal is to detect a particular pattern. So I'm going to, now I have done this many times. So I'm gonna two column again, but even though I still make typo a lot. Two col, and then select file location for my window and copy this, paste over here to complete my conversion into this column form. And for detection, what if I want to detect a signal like, say, this seems to be interesting here, right? So what if I use the signal itself? Like for instance, like this signal itself. It's my filter here. I paste this phi value over here. So this is my filter. And I pick another signal here, say this signal, and put as my second filter, okay? So what if the particular part of the signal, and then we just matrix multiply that, you can expect that we could potentially should have a pretty high response. Actually, no, not this one. I would like to select the entire input like this. All right. So you can see that this is kind of getting a really high signal. Okay. So because that's exactly what I'm selected here from. And then when I do repeat this, actually, I can just extend to where I take as my first matrix in my multiplication. So now I have another signal, which is gray. And gray is picked up this signal where again, this is exactly where I copy the signal from. So it's just to show you that application of detection. If a particular pattern in your signal, you want to detect where it is, they could also run cross correlation across the entire signal. Again, instead of writing your for loop and and then expect that CPU can handle it. If you're able to map that, convert it into this column form, then you'll be able to put it on GPU and perform matching multiplication in parallel. All right, so now I can do something fun and show you that sometimes I study math in the way using this to study that is what might be otherwise complicated math equation. For instance, if you look at the equation of the math for cross correlation, you will see that I have the sigma summation over a particular u minus 101 that if I index through each pixel, I mean each value in this 1D filter, minus 1, 0, and 1. So the equation will be h of u over, and then you have x, which is my signal. If I also index 0, minus 1, 0, and 1, but we also have t 0 to 15. So for cross correlation would be the t is where the signal is 0, 1 to 15, but u plus u is to allow you to select the neighbor before and after minus 1, 0, 1. So this is what the equation is. If you read if I just show you PowerPoint slide, that's what I write on the whiteboard. But then if you want to really study the effect of running this equation across a signal, sometimes I use this technique to just write it down, do some text processing. What does it mean? What I just do I show you what I mean. So I can do something like this. H and H parenthesis and end and then n like this. So I could actually write this h minus 1 in this location. So if I copy this to this location, come on, doesn't let me copy. Cool. So you can see that, okay, now I can see visually this way, when I have h minus 1, that's where this place refers to. Okay, so similarly, I can do something like this. So this term is going to be x of t plus u. What is that? So it's going to be, I can do x parenthesis and I maybe just cut t. T is, what is t? T, I select t. This is t, right? And plus, I actually use some actual math. Plus u. U is here. So this is my t plus u. Didn't finish my equation. Okay, I'm going to, how do I? So I want to select. Maybe I use the mouse to select. So this is my t plus u. Do you see this? G158 and F161 actually is t plus u. And then I go into and do a parenthesis. So it matches my equation. So, okay, I see this is x minus 1, but I can copy over here, but it doesn't quite work because I forgot to fix the f, which is my column for my u index. So I've done this quite a few times now. So in order to fix that location, I just say this. Okay, now I can copy them all to the right. You can see that, okay, now I copy formula. You can see, okay, I see. So this location is minus 1, 0, 1 as a result of t plus u. So I can do the same thing down here, but in this case, I had to fix my 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 158, which is to pick the t row. So I can be then once I have this fixed, let's just review this equation. So I have x t, which is blue, plus u, which is the red, but I fixed the row number 158 and column f in order for me to copy that while respecting the where it is. So what I can copy and paste the formula over. So this is whole thing. You can see that each window now you can see, oh, the purpose of x of t plus u is just like 2, 3, 4, 3, 4, 5, 5, 3, 6. Kind of you can start to see evidence that this equation does refer to this neighbor of this 3. Do you see this? 5, 6, 7, 5, 6, 7. That matches your intuition. So now we can do the coolest part is that I can type out this equation is and now, when I can take a dot product, there will be kind of hard to see. Say H, say this, okay, and this, and plus, and I hope they're doing it right. This and this, and plus, and I hope you know what I'm doing. And this, so I just reproduce the breakdown of the equation. Hopefully it's right. Okay, this 2 plus this 2 plus this 2. I just want to write down in the textual form. So I have this, okay? Now it looks kind of big. Let's just make it larger so you can see the equation. So this is the equation, this dot product of these 3 locations. Now I'm gonna copy of this, but I'm going to fix my B, C, D, I think. Fix B, fix C, and fix D, so I can copy to the right without losing the generalizability of this. Okay, now copy the formula over here. Voila! So this is the way I reproduce this, trying to break down this equation summation over a term. So you can pick anyone to study, whether it does match your intuition. Okay, so this is how I will just show you the way that I tend to approach this really convoluted looking summation or double summation, triple summation who read papers or you study this the math under a particular algorithm, you can use this to help you break it down what the summation really means. And so it becomes kind of quite interesting is that when you read convolution equation, so you can see that it's going to be summation over HU, but it's going to be flipped. So the HU is become minus T. So they can study that as well. So in fact that because I already copied this, so you can see that my U actually flipped over here, but I did not flip over here. So if I do that, I can copy this over here and also copy this equation because it's relative. And then I could do something like this. You can see that the only difference is that -1 now matches 1. And so if I copy all this over here, so we get an updated equation breakdown that you can compare the differences between cross correlation and convolution equation in this way. Okay, so it might sound extremely nerdy, but I enjoyed it anyway. So hope some of you appreciate what I just did. All right, the next I want to talk about another um, common filter called Gaussian filter. That and for so that the purpose of a Gaussian filter, which is in this context, is that I'd like to smooth the signal. In the mean filter, if we have a phi location, we're gonna do 1 over phi each location, 0.2, 0.2. So this is a typical mean filter, 0.2, 0.2, 0.2, 0.2. But what if I like the put a bit more weight to what's closer to the center? So in this case, for instance, I'm raised to 0.4 and my summation is actually 1.2, too much. So I can raise this a little bit, say, I raise it to 0.6. Okay, and then still, maybe raise this a little bit to 2.4. So then we can design this filter. It's supposed to look kind of like a Bell or a Gaussian distribution. There's an equation to actually calculate this particular shape. But I can implement this say too. So show you the effect. I'll do a very quick, come on, one more time. 2 column, and then select file of this, and then copy this and paste over all of them, all the location. Okay, so now I have this, and then to apply this Gaussian filter, discrete Gaussian filter to my signal, now you could know what I'm gonna do is to take a matrix multiplication of my Gaussian filter over the entire column representation of my signal, which for the window size of 5. Ta-da! You can see that it's becoming a bit more smoother here. So this is a smoother version of the input signal. And then you can just play with it because it's live. You can just change this. So we have a really high signal here, say 40, and looks like pretty high peak, but the smoother version kind of smooths down in this way. Okay, so that's what the Gaussian signal does. I'm gonna erase all this. Now, the next is that I like to show you how we could bring up the notch to actually implement a parameterized Gaussian filter. And then, so this is the equation of a Gaussian filter. We have some kind of this normalization term, which is, you can notice that it is, if you have a parameter, let's just mark the number of parameter we need in this case. So the hyperparameter for this Gaussian filter, we have this sigma. That's it. And mu, if we want to have a filter over center, mu is just gonna be 0. Can ignore it. A sigma, do I have a sigma here? Maybe I use this cell to store my sigma, and I'll use this to store my partial calculation. Just make it things easier for our life. So, for instance, I want to do is use to calculate sigma and square root of 2 pi over here. So this one, this is my goal, okay? And my dimension is here. I have the dimension. This is how big I want to model Gaussian. So it's d over here. So let's start with d equals 5 here. D equals 5 here. Okay, my sigma is just say sigma is 2. And this is going to be my sigma times square root of 2 pi. Just sigma here times square root of 2 times pi. So let's just have this radius, so make my implementation easier. Okay. All right. So if I change the sigma, things gonna change. Okay. So now I have a d is 5. What I want to do is that I want to find a way to index through this my u. So -5, -4, -3. I want to generate this sequence kind of like this. That's my goal. So to do that, I will use a built-in function sequence. So I can do is sequence. Okay, and then I have one row, but I have column is actually going to be this times 2 plus 1. Okay, that's how many we need. And I want to start with minus this d, and I want to step by 1. Okay, so this should give me the sequence I want. Okay, minus 5 to 5. Okay, and then so this is our u, but in this equation is x, but I just use u to indicate. So it's because I want to differentiate from my input signal symbol X I use in some other places. So I just use U here. So I'm not confusing people. Now I'm going to write down the equation, but I like to write the first equation just by first focus on this part, the exponential part. And then I can weight this later and to bring the integral sum down to 1. You can see what I mean by that. Let's just do that part. So you put explanation, they're going to have a minus 2 times x. So this become x squared over this is, actually, sorry. This is so ugly. Let's just use a different color. 0. Okay, let me just leave it here for now. No. Okay, anyway, I will just write it out now so I can fix it later. So now I want to do is minus 2, but I want to select my x, which is my u. Select u over here. Actually, I can select the whole range here. This is my u vector, but I want to square this. And then I would like to divide it by sigma square. So sigma is this number, right? This number square. So this is my equation. Okay, carefully written. See if I can success on the first try. I think I did. Okay, you can see that is a bit more getting bigger, but kind of getting smaller. That's what we want. But if I take the sum of this, you might see that if I take the sum of this, it's actually is no, not the sum of this is actually kind of large. I want to normalize this so that that could sum to 1. And so that normalization term happened to be this thing, 501, based on some kind of crazy amount of integral you can try to prove. So if I basically divide this over my sigma times square root of 2 pi, okay, and you get us another weighted down. Then let's just take a sum of g. I denoted g prime and then another one g. Let's just take this just to prove this. This is going to be 1, but not exact, maybe closer because it's a discrete place. So it's 0.99, close enough. You get the idea. All right. So I have this actually visualization here to plot g. You can see that we have this nice kind of bell curve. And then since it's completely parameterized now, that we can see that it's kind of cool. You can change to 7 or 3. You can see this kind of change. But that this figure is up. This figure doesn't change. I can fix that feature. But you can see that this can change 7, that this actually get a larger one, longer one. 3 get a shorter one. Okay. 5 we're gonna here. So now I want to do apply a larger, a larger Gaussian filter. In this case, I have all this. Let's copy this, set this to this one. This is actually 11. Is it 11? 11? Okay, the window size 11. I have not done such a large window size, but no worry because it's easy. So pick 5 to the left, myself, pick another 5 to the right. Okay, so this is my window, and then copy over to my entire signal, like a larger signal, 32 signal, and copy to formula over here. And now I could do is matrix multiplication. Let's just look at the signal again. So I have this large signal to 32, but it's just bigger. And now going to matrix multiplication, the whole thing, and then select the entire signal again. So I can like this. Oops. I want to select the whole signal, not here. So just drag this to the right. Okay, here. All right, so now you can see the result. My blue signal is a smoother version of this Gaussian. Okay, and then if we kind of change the sigma, say 1, so sigma 1, sigma, when sigma is cross variation, you can see that it becomes like a narrower. And so, and my smoother is just not as smooth, but the capture is getting closer to my input signals, which is here. So this is much of a difference, but it's not as smooth. Okay, because you can see these still sharp edges. So if you have a bigger, let's go back to 2, and you can see that it's a smoother now, but the difference is that now you have a bigger gap, bigger difference between your smooth signal and the original signal. So this is something you can kind of play with and to get better intuition. Next, I want to end this just by repeating my ReLU and Maxpool implementation. So for ReLU, so I would like to be able to kind of cross out these negative ones. So the most intuitive implementation is, again, we just do the if, select my signal. If the signal is greater than 0, I'm just going to select the signal again because I'm going to output the same signal. If not, I just output 0 to suppress the signal. So this is my ReLU. You can see that this actually becomes 0, 0, 0. Another alternative implementation is you max each element with 0. So this is the more common implementation to do the same thing, but it's kind of hard to explain. Less intuitive in terms of explanation. You get same result. No, it doesn't get the same result. Come on, one more time. I want to copy the formula over here. Formula. Okay, you can get the same result. I just prove that this is implement as max. This is implement as if and else statement. But this is a lot closer to intuition, what you like ready to accomplish. And now for Maxpool, again, for Maxpool, I actually do want to have a window to each window, pull from the window of, in this six, this case 5, all right, and then copy over here. So I've done this maybe 20 times now. So formula, and then the max pool are going to be max. Pick the max of each column. Each column represents the window, and then I copy this formula over to my actually formula to the rest of location. So now I achieve this. So I have first, you can see the result of ReLU from X to this, and everything's negative is going to just kind of like be 0 out over here. This you can see that it's more prominent here. Let's just change another signal, make it -5 on purpose. You can see that another thing, this one kind of gets reset to 0. Okay, and then you have a max pool. So max pool, then you can see that now here's blue thing become gray thing. Every single window, say this is just going to become reset to the neighbor, the largest value in the neighbor, largest value to the neighbor, and stuff like seems like that. You can see the effect mix pool. Again, this is non-linear. We don't have a linear filter that we multiply with. Also, it's non-parametric because we don't have a parameter we actually select other than the hyperparameter max pool. You have a hyperparameter of the window size, but the itself does not have a parameter that you will typically train for in your optimization function. All right, so this is the end of my 1D filter lecture. Hopefully you use this to help you establish the foundation when we're gonna extend to the 2D filter. You can see how the effect of these filters to images for smoothing, shifting images around, and so on.